Okay, that's it. Okay, thank you, Eric. Okay, everybody, sorry about that. Can you hear me? I'm assuming, let's see. Am I this one?
Mm-hmm. BCC.
Oh, that's the one I want?
One, yeah.
Okay.
Yeah, that's you.
Okay. All right. Okay, everybody.
All right, so.
Thank you for your patience. Okay, I'm glad you can hear me now. We were having some issues with the computer and needed to get some help on that. So we're good. So good evening and welcome to our final Pint-Sized Science webinar. Excited today to talk about our last 3 modules. And before we get too far into that, a couple of announcements. One, first of all, the stipends went out this week. And because, again, they're the final, I should say, the final component of them, we've sent them out in waves. So you should have either received it or you should in the next few days. If you don't get your stipend check by next week, please let me know and I can check into it, make sure that we have the correct address or that there wasn't any issues there. So keep an eye out for stipends and let me know next week if you haven't received them yet. Second thing is you should have received your materials by now. I sent out a document, a Word document that's a receipt for materials. So so that I can verify that you have everything. So if you haven't yet done that, if you have all of your materials, please fill that out. You just have to put your name, your organization, the date, and sign it, even if it's a digital signature, and send that back to me. If there is something that you're missing, I need to know that as soon as possible so that I can get those materials to you, okay? So if you have everything, send that back to me. If you need me to resend you that document, just let me know. I'm happy to do that. If not, if there's something that you're missing, let me know as soon as possible and I'll get that out to you, okay? So those are my 2 big announcements before we get started. Oh, one other thing, I've had some people ask about course for credit. If you are choosing to take this, or if you've already registered, you should have already registered to take this course for credit, then your attendance in the webinar, I monitor the chat room, I take attendance from the chat room, then I know that you were here and that counts for your attendance in the webinar. If you are watching this right now as a recorded version, then what I would ask you to do is as you continue to watch this, is to write a short reflection that includes 3 points of something you found very interesting or useful to the work that you're going to be doing around Pint-Sized Science. Okay, and then you can turn that into me. So you can just send that to me by email. For those of you taking this for credit, the final day for assignments is December 31st. So it included the requirement of you attending the full day training, which you did over the summer, the 4 webinars, which this is the final of those, and then there's some assignments. And those assignments are based on some personal reflections, as well as a lesson plan, a 3 to 5 day lesson plan, all things that are really to benefit you in this process. The assignments, all those assignments need to be turned into me by December 31st. I grade them and then I turn that information into the AEA for credit. Okay, so if you have questions about that, you can let me know for sure. And what I'm going to do now is I'm going to turn it over to David. David is joining us from PocketLab, and I know that we talked a little bit about PocketLab in one of the earlier webinars, but David is here from the company itself, and he's going to give us some instruction and some information on how to utilize this amazing tool for data collection, especially in an early childhood setting. So David, I'll hand it over to you.
Okay, thank you very much. Hopefully everybody can hear me. Maybe if somebody could type in the chat just to make sure.
We can hear you, David.
Okay, great, great. So yeah, I am from PocketLab. Actually, I'm the co-founder, and we started this company several years ago, and the whole idea was to make easy to use, fun and simple but powerful sensors for students to do science activities. So for this activity, the sensor we're using is called a PocketLab Weather. and I'll show it to you, and I'll show you how it works, and then I'll have a short presentation on some things you could do with this. So this is the sensor right here. You can see it's pretty small. It weighs about an ounce. It's very light, and it has a battery inside, and it communicates with the computer by Bluetooth. So it connects to a computer, a Chromebook. I'm doing it on my Mac. I have a desktop Mac. Work on a Windows computer, or work on an iPhone, an Android phone. So you can use it pretty much any device. It connects by Bluetooth, so it's kind of like connecting a wireless mouse. And I'll show you how that works. And with this device, we call it PocketLab Weather. And the reason why I call it PocketLab Weather is it has weather center functions in it. So it can measure temperature, barometric pressure, humidity, light level, and it can calculate dew point and heat index. And altitude. So barometric pressure and altitude are the same measurement, but just two different ways to read it out. And it also has an external temperature probe. So this is just a wire with a probe on the end, and it plugs into the side. There's a little jack on the side, so you plug it in. So it's as simple as that. And you can use this this is fine to put in boiling water. It's good to 180 degrees C, or freezing ice water, or whatever is fine. And you can use this to measure weather, temperature, the conditions in the classroom, the conditions outside. There's a lot of different things you can do. And I'll show you quickly. I'm going to share my screen so you can see what this looks like on a browser. This is a Mac desktop, but if you have a Chromebook, it'll look the same. On the iPhone, it looks a little different, but pretty similar. So let me share this. Hopefully I can do this right here, and you'll see how it works. Okay. I believe you should be seeing a screen with a couple graphs on it.
Yes, we can see that, David.
Great. Okay, so I've connected mine already, so I'm just gonna disconnect it, and I'll reconnect it so you know how this works. The startup screen just has these options. You say, I want to connect, and it'll scan and it'll find your device, which you have a little button to turn it on, and you pair. And now what it'll do is it'll start streaming the data for you right away. So there's different ways to see it. You can have a map, and you can have these data bars. This might be better for younger children. It's easier to see. I prefer to look at graphs, more of an engineer. So the way you select those, I don't want to go too fast here, there's a little squiggly line here that lets you select all the functions inside this sensor. So I'm going to turn off the measurement conditions, and I'm going to turn off the map, and I'm just going to turn on temperature and humidity. You can do up to 3 graphs simultaneously, so I'm just going to show 2. So now this is measuring humidity and temperature, and I have the temperature probe, and the humidity. So for example, if I grab, I don't know if you can see me too, but if I'm grabbing the temperature probe, you see the temperature is going up. I can also blow on the device, and you'll see the humidity will go up. The humidity is shooting up. Your breath has a lot of moisture in it. That's all you have to do. It's very simple. You can record the data. There's a little record button. This clears the graphs, and you start over. So you might have an experiment where you ask the students to, blow on it and collect data. So you would blow on it, and the humidity will go up, and when you're satisfied with it, you press stop, and there's my data. So we're very simple. There's not much more to it than that. And let me see, stop sharing. If there's questions, feel free to put them in the chat, and I'll answer them. And I'll show you in a couple minutes ways you can contact us and reach us if there's support or questions. And of course, the wonderful people at the Science Center of Iowa can help as well too, and we work with them whenever they need help. So let me show you, I have just a short presentation on some ideas for this. So I will share another screen here. Let me see. There we go. Okay. This is a Google Slides here. I'm not going to put it in presentation mode because it takes over my whole screen, and I don't know if that's the best thing. But PocketLab Weather, that's the little blue sensor. There's a picture of it. You can see what it measures: temperature, barometric pressure, humidity, altitude, and as you saw before, it's very easy to connect and use. Some examples that we see teachers and students do: you could attach it to a wall, tape it to a wall, use like a 3M strip or something like that, and it could be your little weather center. And you can use it to collect. You can collect all the data on it simultaneously. So if you wanted to collect data for a whole classroom period, you could do that, and then maybe look at the data later for a whole day or whatever. And like, for example, you can start at the beginning of the class. This is some data actually from a classroom. And you can see as students come into the classroom over time, the humidity goes up because you have the activity and everybody's breathing and so on. The temperature, I forget exactly what that was. I think it was the heater or the air conditioning kicking on or the heater kicking on, the light going on and off in the room. You could see, for example. So you can have the students, you can give them activities where they can you collect the data and examine the cause and effect. And this could be a lot of fun for them to kind of test different things out. Another thing we see a lot of teachers do, we see a lot of this, actually, if you go on Twitter, you'll probably see hundreds of these that teachers have done, is to look at the effect of heat islands. For example, you can take the PocketLab out and go measure on the asphalt in the parking lot, then maybe go measure in a grassy area and look at the differences in those and kind of see what is going on and how big is the difference. And for example, you would have students make a prediction. How much warmer is it in the parking lot versus under a tree in a grassy area? And they can make predictions and then go out and collect data and test it out. So there's a lot of fun things you can do with this, a lot of creative ideas. And here's an example of some data that somebody collected from a heat island. They use it, this is an iPhone, so you can see the iPhone interface here. It looks very similar. And they measured, in the grassy areas and then out in the park. So a lot of really simple things you can do. We have a lot of other creative ideas on our website. We have an educators tab on the website, and there are all kinds of different lessons that you could use. And of course, the Science Center has wonderful resources and wonderful ideas on things you can do with this. And just the last thing I'll leave you with here is the information. And we have our educators page. We're on Twitter, Instagram, Facebook. We have a support. Email is the best way to reach us. We answer very quickly, and we're happy to help out with any issues or questions or things you have for implementing. So that's basically it. If there's questions, I'm happy to answer anything, or you know how to reach us on email or from our website.
David, I have a question. This is Jolie. I had a teacher ask me earlier this week about whether or not the PocketLab can be outside and in what environment outside. Like, what if it's raining or snowing? How does that interact with the PocketLab device?
Yeah, this is a great question. Okay, so in order, it's I would call it water resistant. It is not waterproof. So in order for us to measure humidity, for example, we have to have airflow inside it. And you can see there's openings on the side. There's no opening for the humidity sensor and so on. So what people usually do is put it under the awning. It's going to be fine under the awning. It's actually pretty durable. If you dropped it in a puddle, I think it would be okay. I think if you let it dry out, it'll be fine. If you dunk it in water for a couple hours, you're out of luck. It's going to ruin the sensors inside. So we do have a lot of people who put them under the awnings. That's the best place, or right outside a window where it doesn't get, rained on or whatever.
Awesome. Thank you for that, because that's kind of what I thought. So I'm glad I was able to confirm that from you. Anything else that you want to share with us about the product, or other things that you have that might be of interest to these teachers?
So we do, just a couple quick things I would love to tell you. We do have a, and you know what, it's in my other room. Well, hang on one second. I'll be right back.
Okay, while David stepped out, I'll just share with you that I met David personally at NSTA, the National Science Teachers Convention, and he was excited to show me some of the new types of sensors that they have, and I'm excited that that's what he pulled out to show you.
Thanks, Jolie. So we have another sensor it's very similar to this. It has an orange cover. So it has all the weather functions, and it has on top of it motion functions like an accelerometer, a gyroscope, magnetic fields, and that's called PocketLab Voyager. And these are on our website. You can order from us easily, or send us a message if you need quotations or whatever. If we're talking about the environment, we just this year have introduced this new device. This we call PocketLab Air. I'll bring it closer so you can see it. It's a little bit larger. So it's weighs maybe about twice what your cell phone does. And you can see it's a little thicker. So this actually measures CO2, ozone, and particulates. And particulates would mean smoke, like from fires or dust from construction. And we've targeted this specifically at climate. So it works exactly the same. You just open a browser or your iPhone and connect. You press a button. The graphs look exactly the same, but they're just different sensors. So one thing we have a lot of students doing with this is doing things like, for example, you go out to the drop-off where parents come and drop off the kids, and measure the CO2 when everybody's there, and then measure it during the day, and you'll see it's much lower. So you could do interesting things like that. Here in California, we have a lot of wildfires. It's always in the news. And you can measure the particulates, and you can correlate this very easily to the local AQI data. So we have Bay Area air quality stations, and this will correlates very well to those, but the big important thing is that we only have a couple of them. Even in the Bay Area, we have like San Jose, San Francisco, Berkeley, and they're 50 miles apart. This lets you collect data anywhere, obviously, and kind of fill in the gaps. So this is kind of a cool thing if you're thinking about climate and environment. And then the other thing we're doing to try to help make your life easier is we're creating an online lab notebook. So you can collect the data online, and as a teacher, you would be able to assign students to lab groups and create lab activities for them that they could do digitally as opposed to doing in a physical lab notebook. So those are the major things we have coming.
Thank you, David, for sharing that. I was telling them as you stepped away that I was hoping you were going to talk about the PocketLab Air. I think it's some of the teachers that we have on this call or that are participating work with older students. Some work with young students, 3-year-olds, where this maybe wouldn't necessarily speak to them, but some work with older students. And I think that air quality is an issue in Iowa, but it's very different than the issues we have in California. And I'm fascinated to think about pollen counts and particulates in the air here. And even during harvest. So now it being harvest season, and as the combines are out and they're harvesting the corn and the soybeans, what does that do to the air quality and how does it change? So I think that there's some really wonderful opportunities for a device like that for people in Iowa to kind of research it and study it. And if they happen to have the PocketLab Weather, they're already familiar with that, this could be an addendum. It would be another component that maybe their students could use to investigate it into more depth.
Yeah, it works just the same. You know, if you can use one, you can use the other. We have a partner, a school we partner with in Chico, California. Chico is very rural. It's all a farming community. And if you recall the news, it was almost 1 year ago today. They called it the Paradise Fire. These were horrific fires that happened in Central California. That was the area. I went up there, and we have teachers who are very good friends, and we work with them, and they piloted these. So they have exactly the same issues. In the fall, they have these big burn-offs of the brush. They have harvests, they have pesticides, all different things, and they're using these to kind of monitor around the schools and the environment and some people's homes and things like that. So it's great for that. And there's no other way to get that data easily or inexpensively. So it's really interesting. And the kids driving it, where we see them kind of able to, you know, the kids to kind of drive the collection is around 4th and 5th grade. I think younger than that is a little hard, but around 4th and 5th grade is no problem for them to kind of understand, you know, and collect the data and monitor it.
I really appreciate you sharing that, because I think it's important for students to have the ability to gather data themselves and not just read about it, but understand the process of gathering information and then forming ideas, additional questions, possible answers or solutions to a problem based on that data. And so I think this tool, PocketLab, is a really great way to introduce even our young learners to the idea of gathering data and using technology to do that. So thank you so much for your time today and for sharing with us. And I know that you put up on that Google slide your contact information. And I certainly, if anybody in particular wants to learn more about anything that David was talking about or any other products, they can connect with me, and I can certainly pass them on and connect them with you.
Yeah, by all means, you know, and however you reach out to us, we're happy to help. In the chat here, I'm going to post just for fun. You might enjoy everyone when you have some time. This is a 5th graders in Boca Raton who did exactly this drop-off experiment with the PocketLab Weather, and they got written up in the local newspaper, so they were so excited about that. So I think 5th grade is fine. 4th grade is fine. They can start to take control and you know, and you know, collect some meaningful data that's really interesting to them and meaningful to the community and to the school. So thank you very much for your time. Reach out anytime. We're always happy to help.
Okay. Thank you so much. Thank you, David. Okay. So we're back. I'm really glad that you got a chance to meet David and talk to him and hear what he had to say. Like I said, I met him at NSTA, and I think it's really exciting that there are companies out there that are using technology to support science education. And so I just wanted to showcase that and be able to share with you those kind of things. So let's go back to our PowerPoint here. And let's look at what we're doing today. We were talking about PocketLab, and we are going to continue to talk about our 3 different modules for today, the last of the 3. So we're going to look at exploring engineering, push and pull, and fascinating farmers. And I know that not everybody on the webinar has all 3 of those because you selected one of them. But I hope that as we're discussing these, the modules, that we're always learning and gaining ideas of how to support our flower model. So remember, we learned about this during the training and this idea of growing a scientist. So how do we begin with a seed, right? So this is a moment of inquiry, of a phenomena, a provocation, something that stirs student excitement, wonder, and curiosity. And then how do we water that through questioning? So allowing students to generate a list of questions, and remember that during our trainings, we did that with the bouncing ball activity, and we categorized those questions as being testable or researchable. It's not necessarily what you have to do every time, but it's good for students to understand the different types of questions that we can ask and how we might proceed from those types of questions. And then once they generate some of these questions, how do we grow that? So this is where they do investigation, and they might use something like PocketLab to do that, to investigate something, to collect data, and to challenge some of those questions. So that's that growing. And then as they grow it, we begin to see the blossom from that experience. So these are results, authentic work, representations, findings. I'm excited to look at the document that David posted about these fifth graders studying the pickup lane at school and what happens to the air quality during that time, right? So what are they finding out? What are those conclusions? And then of course the harvest is that opportunity to share it. So them sharing it in the newspaper is a really great example of how students took that question, investigated it, came up with a conclusion, and then how are they sharing that with others? So as we go through each of these modules, I just want us to keep in mind our flower graphic and remember that we're trying to grow a scientist and that scientific thinking that is just so natural for our young learners, and we want to support that through materials and opportunity. So we're going to start off by talking a little bit about push and pull. So what I did here is I put in the cards that you receive for your kit, there is, or for your module, we put always this kind of a general web. It's a shortened web. If you go onto the website, the Pint Size Science website, you will see an extended version of this web, but this is just a short one to kind of get you started. And I always want to point out here that you will see these three main topics, or three, sometimes they're four, topics that module is working to address. So in push and pull, we're trying to look at the ideas that an object can affect other objects when it's in motion. And there's an idea here for a phenomenon that you could do, that you could begin, and then here's some structure for how you might investigate that. And the materials for this can be found in your Science Sprouts kit. So anyone can do this. Anyone can be looking at how these different balls, very similar to the bouncing ball activity that we did, and look at that idea of gravity and motion. The whole point of this module is to look at things that create a push or a pull. It's not so much the focus of like magnetism, even though there's magnets in the kit. It's not necessarily about how magnets work, but it's the idea that magnets can create a push or a pull. So if we're talking about the pull of something to the floor, we can talk about that force being gravity. And they can investigate that of how gravity affects the pull of various things. So if you have a real golf ball, a foam golf ball, and a wiffle ball, which you all received in your Science Sprouts kit, then how do those react differently, if they react differently, to the force of gravity? Begin with questions. Ask them to make predictions on what do they find out, and they can vary the way that they experiment with that and learn more as we go through that process. Another topic in push and pull that we're looking at is that a change in motion can affect the speed and or the direction of an object. So when an object is in motion, or even when it's not, something else can cause that motion to change. And talking about speed and direction is definitely something even our young learners can understand. They can understand that something can move slower or faster, something can stop and it can start. Those are all examples of speed, right? Or change in that speed. You can use the word acceleration if you want to, but you don't really need to. They can understand those basic concepts. And the idea of direction, of does it change in direction? And we can certainly support our concepts of going to the right, going to the left. We can even use cardinal directions if you want to use north and south, east and west, that we can introduce that idea of direction. very much supporting those concepts in the early childhood. So you see that idea, and then also just the fact that push and pull are both forces. And remember, we talked about this last week, that we don't necessarily have to teach the students all of the physics in this case. Push and pull is really a physics module. They don't have to understand all of those physics to be learning about the concept of push and pull. They can experience it. That's the whole point of inquiry-based learning. So the more opportunities that we provide them to experience push and experience pull, their minds are naturally going to want to make sense of that and begin to learn. And as they get older, we can add more experiences on top of that and build on that knowledge and that understanding. So the more opportunities we have for them to authentically learn about these forces of push and pull, the better they're going to understand it in the future. And we can continually add more vocabulary to the process. You yourself do not have to be an expert in physics to teach this module, but I want to show you how we are trying to support you to be more comfortable in the process. So again, you see here that basic outline, that basic web, and here's an example of an activity that is in this kit. So this is air pressure versus water pressure. I would tell you, as somebody who is taught at the collegiate level, I would teach this lesson with elementary students, certainly with preschool students, elementary, junior high, high school. I also taught many years at a high school setting, and I would teach this in college too, because you can build it. This is a layered understanding of pressure and forces and push and pull, and how water can do that and how air can do that, and how do they do it differently. Okay, so what we see here is just this general idea of materials that you would use, the syringes that come in the push and pull kit, and having access to things like water or other kinds of fluids or liquids if you would like. And then the golf balls and the foam and the wiffle balls that we just talked about in the previous experience that are also in your Science Sprouts kit. And we can use those to understand the push and the pull that can be created by air and water. I want to point out to you that you see some very basic, very general directions, and the questions, some prompts that you can use, are always in a contrasting color. So you can kind of quickly see those. And this one says, how does the syringe system work with water? And does that have more force than if you use it with air? Right? So these are some prompting questions that you can use in this experience. Remember that over here on the right side of the card, we see this idea of sprout versus seedling. So remember that sprout is for our even younger learners. So these might be our 3-4-year-olds. How could you modify this? Versus seedling, which is kind of an adaptation for our older students. Okay, these are just suggestions. And then on the back of that card, we see here some background information. So where necessary or needed, on the back of an activity card, you will see some science concepts to give you more knowledge and understanding in the concept that is being taught in that activity. So what we see here is some information about how water acts differently to pressure than does air. And that is based on the concept of it being a liquid versus a gas. Your students do not have to have that understanding. I'm not saying that you need to teach them that about gas having variable volume but liquid having, a constant volume. You don't have to get into that, okay? But they can experience that through these materials, and you can be more confident in providing that activity if you understand it a little bit more at that level. So as it's talking about here, that liquids have a constant volume. So what that means, I'm going to, let me read through this, and then I'm going to switch over to the camera so I can show you the syringes a little bit. But liquids have a constant volume, which means you cannot compress them. That's why, for example, blood pressure in your body is so important. So the liquid that flows through your arteries and veins has a pressure to it, right? Your blood pressure. And it's in a contained system. You cannot compress that liquid. It maintains its own volume, and it has a constant volume, which is why you can use it for pressure. So you can push on that liquid, and that push travels throughout your entire body. So think about the push that comes from your heart, and it starts obviously in your heart and pushes that blood through the arteries all the way down to your toes and all the way back up to the heart again. That happens because liquid has a constant volume, and it allows that liquid to maintain that push, right? That force. Gases do not have a constant volume. They can be compressed, okay? So they react very differently and create a very different kind of push because they can be compressed, okay? So that's kind of what it's talking about here in this background science. And if you want to, you can introduce the vocabulary here of this word hydraulics. So hydraulics is based on liquids being able to transfer pressure, and pneumatics has to do with gases being able to transfer pressure or a push in it. So if you wanted to introduce those, you could. You certainly don't have to if you don't feel like your students are ready for that, but that's just kind of an introduction really into the physics behind it. Okay, so I'm going to transfer now to my hover cam. So hopefully this is going to work. Okay, yay. So what we see here is a collection of syringes and some flexible tubing that you got in your kit you received. But even if you didn't get push and pull, these are things that you can easily have access to. These little syringes right here, I just went to the Walmart pharmacy. Sorry, I know it's trying to autofocus. I just went to the Walmart pharmacy and asked for some. These are the syringes they use for medication, which is a fabulous way to introduce this idea to kids because many of them probably have taken liquid medication using a syringe. So you can even talk about that, right? That's a previous experience. How you draw the liquid up into the syringe and then how you push on this part to push that liquid into their mouth so that they can, drink that and take their medication. But it can also be used with air. So I have a system set up here with these two different syringes from Walmart, and they have marks on them to measure. And it's really interesting because you can certainly measure the liquid with here, but we can also generally measure gases that way too. Okay, so what can happen is if I introduce air into this system, okay, then if I push this, then you see this syringe move. There's a push, right? Talk about a phenomenon. Imagine if you set this up for your students and you say, I push this syringe here and it causes this syringe to move. And then we might follow up with a question of, can I make this syringe now cause this syringe to move? Okay, so if I push on this one, it did. It caused it to move. So these are both examples of push. We can even then investigate the idea of pull. So if I pull on this, does it cause the syringe to move? And it does. So the same device, we can create a push and we can create a pull. Okay, very simply. And then our students might be super excited about that, and we can investigate what is causing that. What is inside of here that is allowing us to push and to pull? And just by looking at these tubes, they might say there's nothing in there. This is the beauty of science, because we can see that there is proof that something is in there, even though we can't see it. And we can introduce this idea of being able to measure air or a gas. Even though we can't see it, we know that it is in here. And we can see that when we do our push and our pull. It's evidence of the gas being inside of the tube, okay? Then you can start to do some really cool stuff and maybe substitute this air for water. So what if we were to put water into this system and we could ask them, how do you think it might react different? Will it be the same? Will it be easier or more difficult to push or to pull? Does it affect it? Okay, and remember, you can do this with our large syringes too. You could even substitute, right? So you got multiple sets of syringes. So you could mix and match. I'm trying not to be able to get that one on here. I can maybe put it inside of here, right? So now I can mix and match. So now I have a large syringe and a small syringe. So how is that going to react? What will happen to this situation? Okay, they can naturally experiment. If you have a center, maybe if you have a water table, you could put these pieces in there and have them just naturally investigating that. Okay, and what might be super fun for you to do is to take this tubing and you might intentionally cut it. Because if you cut it, you will find that this push and pull doesn't work the same as it did before. In fact, it's very difficult to get your push and pull because you will have things leaking out of this cut. So we can talk about how that affects the push and pull. You could even talk about, if you wanted to talk about inside of your body, this is why it is dangerous if you get a cut, because now we have a hole in our tubing and blood can come out and we lose pressure. So you could compare that to this internal pressure push and pull system that you have going on inside your body. That's definitely something for our seedlings, our older students, our younger students, our sprouts. We could just play with the syringes as is. And the activity talks about putting one of the golf balls here and seeing if I can make that golf ball move without touching it. So then we might take our syringe and push and see if what's coming out of here can cause one of those balls to move. And we can try it with just air versus if I put water in here, can I get the golf ball to move? If I put water in here, okay, which one causes more push? And what if I have a bigger syringe? Does that cause more push? Can I do a pull? Can I cause the ball to move towards me if I pull in like this? So much experimentation. Again, they don't have to fully understand the science behind it, but with these simple tools, right? And maybe some of this plastic tubing and some of those golf balls that came in your Science Sprouts kit, students can learn a tremendous amount about the forces that can create a push or a pull. Okay, just through that experimentation. So I want to go back here to my PowerPoint. Go back to this. Okay, and then I want to ask you, maybe, where do we see examples of this in real life? So I shared with you the idea of talking about your heart and the arteries and veins, which definitely is a concept for older students, maybe not for younger students to fully understand that, but that's one example. Are there any other examples you can think of this idea of this kind of push and pull in real life based on either hydraulics or pneumatics? This is a pause so that you can think about that. And if you're interested in sharing in the chat room, I would love to see it. If you can think of any real life examples of where we might use water or air, liquid or a gas to create a push or pull. I have an example for you. How about this?
Introducing the JetLev R200, a groundbreaking flight system that shatters the limitations of every flying machine before it. Your flight begins as a 200 horsepower marine engine pumps water up a 10-meter hose at over 1,000 gallons per minute, generating over 420 pounds of thrust. When the water reaches the ultralight backpack, it's directed through two nozzles at up to 60 psi. Aiming the nozzles creates smooth, stable turns, And the motorcycle-style throttle lets you climb, dive, and hover up to 30 feet above or below the surface. As you fly, the boat follows, in salt or fresh water, even in the shallows. The 5-point safety harness and trapeze keep you in optimal flying position, while the fuel-efficient motor gives you hours of flight on a single tank of high-octane gasoline. It's surprisingly smooth, quiet, and easy to use. Make history by flying a JetLev today.
Okay, I'm gonna pause it right there. How cool would that be? I thought that was such a great example of a push using pneumatics, using a fluid. And what I found really amazing about this that I didn't fully understand is that I've seen these before, but there's a little boat. I don't know if you saw it, but there's a little boat back there, and it's hooked up to this tube, and that boat is drawing in water and is pushing the water out through these nozzles, okay, which is creating a push. And it's at such a great rate that it is lifting him above the water. All right. And it actually would allow him to move under the water too. I don't know if you caught that, but he could be moving almost like a dolphin under the water as well, at a high speed using the same pressure. So it's an example of a push or a pull, in this case, a push, being used by a similar system. Okay. So I found lots of videos online. This was just a really simple, it's kind of an advertisement for this company, but I thought it was a really great example of how you could use this. And they would feel like superheroes, right, if they were able to do that. So that is our kind of our look at the idea. Let me go back here for a second. I just want to go back to our idea of push and pull. Some of the other things that are in this module, remember, that you can use are things like magnets, and we provided you a variety of magnets. So imagine that you might ask students something similar about moving things toward or away based on magnets. And I think a beautiful example of that are things like the maglev trains that they have in Asia. So they're using, instead of wheels, they're using magnets for trains to basically float on and to move very, very fast, right? So that's an application of that idea of a push or a pull using magnets. But I think it's really amazing that you can use those variety of magnets and see how you can cause things to move. It's a force, right? We're not necessarily studying how magnets work, but that you can create a force, a movement based on those magnets. And then of course you have the ramps, and the ramps are an incredible way to study how a force such as gravity can affect a push or a pull. And the ramps, remember, come with those varied textures. So you can even look at the force of friction and how does friction affect the pull of gravity of things towards the earth, or how you could push things. Right? So you got in your magnet kit, you got a couple of those little cars. So what if you put the cars on that flat material that the ramps can have? So don't put it on the ramp, just put it on a flat surface and put your little cars on there and see how does that car push or pull from the magnets based on the different texture, which is really a measurement of friction, which is another force. Again, your students don't have to fully understand that, but they can experience that. And I think that as winter is coming and things are freezing and getting cold, ice and snow are always a wonderful way to study push and pull, right? And think about the effort it takes to pull yourself back up the hill after sledding versus going down the hill, being pulled by gravity that way, or pushing things around on ice. So is it easier, more difficult, or the same to push things on an icy surface than it is on a surface that it doesn't have ice in it, right? So maybe the sidewalk or something like that. all of these are about the concept of push and pull, right? The forces behind that. Okay, so now we're going to move on and talk about our next module. We're going to talk about engineering. So exploring engineering, we came up with kind of 4 different topics for exploring engineering, and we're going to kind of talk about them a little bit here. So first of all, that engineers use tools to solve problems. And I brought with me the Maker's Toolkit, so I'm going to go through that and kind of show you what those tools are for. But remember, even if you didn't get this kit, think about different tools that engineers use. And it could be from measuring things, you know, like rulers or protractors, to tools for moving things, for categorizing things, for changing the shape of things. Those would all be examples of tools. That the shape of an object is related to its function. Okay, so I gave you here a list of things that they would quite possibly see in their everyday life: binder clips, tweezers, clothespins, and scissors. How are they similar and how are they different? This would be a great provocation, right, for students to look at and explore how these different things have similar actions, but have quite different purposes. You wouldn't use scissors to hold papers together, right? And if you have a splinter, you wouldn't want to use binder clip to pull that splinter out. But they still all have very similar components. So having a provocation where they investigate the similarities and differences between these is a really great way to get them to think about that. And we'll talk a little bit about the Grab Lab activity in just a little bit. So failure, another point is that failure is a way to access success or to assess success. And learning almost what doesn't work can be more valuable than what does, because it teaches us so much about it. And so the idea, here's a suggestion about designing a chair. Students are very familiar with chairs and probably use them on a daily basis, but what makes a really good chair? And they might design their own chair and build it out of cardboard. So you could use the make-dos that came in this kit for them to design their own version of a chair, right? And think about what would be good. Does the chair have a back? Does it have legs? Is it tall? Is it close to the ground? How wide is it? All of those things are points that an engineer would look at. And that engineers also use the design cycle. So they go through this idea. We're going to look at this book, Going Places, that came in your kit, but they look through materials and understand the process of designing and saying, you know, what is it I'm trying to do? What are those next steps I need to take? Let's try it out. Let's evaluate how it went. And then maybe I need to go back and change something and do it in a very different way. So these are the 4 main ideas that we're working to accomplish in exploring engineering. So I want to talk a little bit about the book that came in here. The book one of the books that came in this is the book called Going Places. And this video is actually, it's called Above and Beyond. You can find it on YouTube, but this video is kind of that book in cartoon form. And so we're going to watch this. And something I want you to think about is that in this engineering kit, you received materials to make grab labs and also sail cars. And we're going to talk about that. And I have a lot of teachers who tell me, how do I make these, or how do I have students make these? And I want you to just keep that thought in mind. We're going to talk about it, but I want you to keep that in mind as we watch these videos and think about this idea of kits and building things based on kits. Okay, so I just want you to keep that in mind as we watch this video.
It was a warm spring morning down at the Main Street schoolyard. Excitement was in the air. "Hey, check this out," said Charlie. "The school's Going Places contest has been announced. Come on, let's go get our kits." And so the kits were handed out. Everyone identical. Everyone with a set of precise instructions. Each student set off to work. Charlie knew how to follow directions. He made great progress and was quite proud of his work. Meanwhile, Maya was taking her time. She watched the world around her, noticing other ways things go places. The next morning, Charlie was finished and carefully inspected his work. But a noise interrupted his thoughts. "Wow," said Charlie. "What is that? You didn't follow the directions, did you?" "I started to," said Maya, "but I wanted to try something different." Maya, what does that have to do with a go-kart?" asked Charlie. "Who said it had to be a go-kart?" Suddenly my project doesn't look very exciting." "Oh, but you're a great builder," said Maya. "Hey, maybe we should work together." And so they did. First, they compared notes. Charlie was good at details. Maya, good at dreaming up ideas. Each had a different approach to getting things done. Then they got to work. Side by side, they helped one another to build something new, something inspired, something spectacular. The next morning, everyone gathered for the final challenge, the big race. Each student stood alongside his or her finished project, each cart a perfect replica. Well, almost perfect. "Ready?" asked Charlie. "Ready as I'll ever be," said Maya. Some of the other students weren't so convinced. "Ha! You may think you're going places, but you're just going to lose."
Students, start your engines. On your mark. Get set.
Charlie shouted, "Maya, they're all ahead of us. What are we waiting for?" "No worries," said Maya. "Flaps down, throttle up." What? Whoa, did you see that? And we have our winner. Charlie and Maya were ecstatic. "We did it. We finished," said Charlie. "Finished? I don't think so. We've only just begun." "Right. Flaps down, throttle up." And off they went. They really were going places. They were going above and beyond.
Okay. I truly enjoy, oh, sorry, there's. I love that little quote at the end. I almost cut that part off. So this video is based on the book. And I love that Kat was talking about in the group chat, Kat was talking about how this is good for social, emotional, and the idea of perfection and discussions on that. I think it's such a wonderful story, going places. And from the idea of a maker, what I appreciate is that the students in this story were all given a kit, right? A basic kit. Everybody got the same, and their first instinct is to all build the same thing. But how are we going to look at things differently, and how are we going to solve the problems of the world? And an engineer is going to look at that kit and say, well, what else can I do with it? How else could I use that? What are the different things that I could do? And that it's that mentality, that problem solving mentality that we want to grow in our students. And not just students who are going to be an engineer someday, but students that are going to be functioning people in our community, right? As how do we solve the problem? How do we look at it differently? And not just take the kit and make what everybody else is making. So along those lines, I want to point out that in your module, your Exploring Engineers module, you received some materials to build some kits. And there are two of them. One is called the Sail Car and the other one is the Grab Lab. So I want to talk a little bit about this, and I have a lot of teachers who ask me about this, about using the materials and how do we do it with young learners, and you know, do you have the students build a car? How, you know, do you build the car first? So let me give you some thoughts and ideas around this. Okay, and I've included some information here from the website from Teacher Geek. So Teacher Geek is the company that we purchased these from. And earlier today, I sent an email out to all of the people that received Exploring Engineering and sent you the links to their building instructions from their website. They have a really great website that gives you lots of information and support in using these materials. But I just want to show you, so here's a picture of what these sail cars can look like. So I just want you to imagine this, right? I'm going to show you basically how to build the car part of this. And the idea of the Sail Lab, turning it into really a lab, is for the students to investigate how they can get this car to move farther or faster or easier based on the type of sail that they put on it. So this module included a fan. So there's a desk fan, right, that you can put on your desk. So the idea is that students can build some type of car that has a sail to it, and then they can investigate how does that sail cause the car to move. You know, does it move farther, faster, slower? Does it move in a straight line? Based on the way that I put the sails on here. So the plates that the sail is made on have all of these options to put the sails themselves in. So it comes with the dowels, right? It comes with the wheels, and I'm going to show you this part here in just a minute of how to build a car. But even once the car is built, right, students can experiment with how many sails they put on here, where they put the sails, the shape of the sail. And the beautiful point is there is no one right answer to this. This is how an engineer thinks. This is how you use the design process. So your goal is to create this car that is movable by wind, let's say. Maybe that's the challenge, right? And the students can come up with lots of different ways to answer that challenge or to work towards that challenge. They don't have to take the kit and all build it exactly the same like they did in the book or in the video that we just watched. They can create their own version of it. We have a very similar experience to this at the Science Center in our makerspace, our makers exhibit, except it uses magnetism. So it looks very similar. They have an opportunity to use different types of poles, if you will, and different size materials to create a sail. And there's a fan, but instead of it moving on wheels, it moves on a magnetic surface so that it slides. So it's like maglev, like we were talking about the trains. So we have something very similar to that. So I want to show you some of the pieces that came in your kit. Let's see. Right? Okay. So in your kit, you received the maker tool set. I don't know if I'm gonna, right? This is the maker tool set in this box. And these are the tools that you received. They are real tools. They are just smaller and easier for young hands to hold on to, but they are still quite heavy. The hammer, I don't know if you've tried it yet, but it is heavy. This is a heavy hammer. It is a real tool for kids to use, but I really enjoy the grip here that makes it easier for hands to hold on to because it is heavy, okay? This tool right here is maybe one that the students might not use, but you might use. It has a release right here. It has a safety, sorry for the auto focus, right? To allow you to open and close. And the idea is that you use this to cut things like the dowels, right? So in making the car, you're going to cut the dowels at a certain length. So you would put this in here, you would measure it out, and then you would snap this and it would cut the dowel. Okay, and the directions are going to tell you how long to make that so that it can become the axle for the wheels. But what's on here and you probably can't see it through the video, but there's measurement angles here. So if you wanted to put this dowel at an angle, we can create beveled edges, right? If that was needed or necessary in how you were using it. But then pulling this handle down and then it would snap that. So this is probably a tool that students wouldn't use, but adults would, but they can still, you know, have the adults cut it the way that they would like. And then you can push this closed like that, right? So that the blades stay closed, which is a safer way to store it. Okay, this tool right here, I'm gonna show you in the directions, is for widening the circles in here. So the post that you wanna make with the dowels, you use this tool and you push it in here and it kind of routers out that hole so that the dowel would fit in there, or the holder would, or something else. So that's what this tool is used for. Then you see there's a Phillips screwdriver. The kit, the sale car kit comes with screws. So you can use this screwdriver for those screws. And then it also has a pair of pliers. And I want to show you these pliers. Okay, again, they're real pliers. They're heavy. But I want to show you this side right here. Okay, so they're kind of like channel locks, and that you can open and close them here. But this part, we can slide this over, okay, if I open it, and now it allows me to hold on to something that is bigger, right? So if I needed to grab something that was bigger and still get that tension on it, or if I'm trying to hold on to something that's smaller. So that's why it has that variation right there. Okay, so those are the tools that you're going to use in conjunction with the directions. So I want to show you the directions here on the sale card. So this is the handout that I sent to you. It's on the Teacher Geek website, and it's going to be on our website. We're just having some issues with our website right now that's not letting me upload things. So that's why I wanted to send it to you. But this is exactly what the directions look like. They talk to you about the two different plates and how to screw those together. Here's the screwdriver, right? And then here's the reaming tool. So in this case, you're going to ream out the holes down here for putting the screws in, okay? Then it shows you how to use the cutting tool, and it tells you exactly how long, so you can cut that dowel. Then you see using the hammer to tap the dowel down into the wheels. Then you're going to put the wheels into those plates as you just set them up, right? Where we reamed the holes, we kind of widened the holes. And then you've made the car, and it tells you to make sure that the wheels can spin. And if they don't, then you may have to ream that a little bit more. So let me show you again, kind of what they're talking about, all right? So these are the plates. So they're telling you to put these plates together, and then you're going to ream, oops, not the screwdriver yet, but you can ream right in here and then use those screws to put those screws in there. This is for the hole, sorry, this is for the dowel, right? So that the dowel fits in here. And then here's where the screws go. So you put them into the corners to hold the plates together. And then the dowel is going to go through here. And then the wheels will go here on the end. Okay, very simple, right? And then you build the basic car. And the students now can experiment with the car and adding a sail, for example. So there's some little plugs that come with the dowels for putting this in here. And then they can design the various types of sails so that they can experiment with it. Okay, it is not difficult to do. And for some of our younger students, you might, like I said, you might build the cars for them and then have them just work with building the sails. So they could use lots of different materials. They could try using regular paper or tissue paper. They might use like a plastic bag. They might use cardboard. They could try all different kinds of things. And then they might experiment even with how many sails or where they put the sails, right? To get the most out of the wind that's blowing from the fan. The fan has multiple speeds and it can also be tilted. So you could even experiment with that too to see what is the best way to get that to move. Okay, the other kit that comes in here is one, it's for a grab lab. And it's basically for creating an articulating device that allows you to pinch things and pick them up. So they're linkages. Again, there are directions that I sent you all and that are on the website that kind of show you how to basically build them. But then what you can do is alter how long the linkages are, or maybe even what you put at the end of the grabbing tool. So they suggest a variety of different tools to help that tool to grab different kinds of things that are small or things that are delicate, things that are heavy. So how might you alter that? Think like an engineer, build like an engineer, process, practice, try things out like an engineer. So you do not have to come up with these answers. You don't have to say, this is what we're going to do. You're going to let the students authentically experiment and figure that out. That's what we're trying to get them to come to, is that point where they are investigating that. Okay, so again, here you can figure out how this would work best for you. If you're in an elementary school, you might ask your first, second, third, fourth graders to build the cars, and maybe they come down and do a shared activity with the preschoolers on how to investigate, right? The way that wind works, or the way that a grabbing tool might work. How is that similar to an animal's that grabbing tool? How is it like an animal's mouth or a bird's beak, right? That you can make comparisons. So you could do it that way, or you could have the students go through an experiment and practice building these actual, the actual cars at the grab lab. So, you kind of have to evaluate where your students are, but this is the beauty of engineering, is them going through that design process. What do you want to try to make? What do you think is going to happen? Let's design that. Let's build it or make it. Let's try it out. Let's evaluate it. And then let's see how we did. Remember, in your Science Sprouts kit, you got things like tape measures. You got rulers in there. You have, remember, a scale. So you can even weigh your car and see if that has anything to do with it. Maybe students want to add weight. What if they put a chunk of Play-Doh on the car? Does that make it move better with the sails or not? You can use various different things from your Science Sprouts kit to measure the effectability, the stopwatches, right? You receive stopwatches. So you could even look at which car will go faster, which will get to this designated point at a faster time. And they could use their stopwatches to measure that. Lots of different ways. And take your cue from the students. You might build the car as a phenomenon or a provocation to get them started, but let them take it to the next level. Let them ask questions, and then you provide them the opportunity, the materials to investigate that question and learn more about it. Okay, so that's our exploring engineering. Yes, Lisa shared that Teacher Geek has lots of great examples they do, and they have lots of these worksheet kind of things, like the directions that I just showed you, like this. They have lots of sheets like this that give you instructions, very simple directions, but also ideas and challenges. So how you might take it to the next step, or what else you could do with it. And you can, if you're interested, you can purchase more materials like this. So you can purchase just, the whole plates. If you wanted more, you can purchase just the dowels. They sell things in kits, but also very modularly, just what are the pieces that you need. And we've been working with them for a couple of years now, and I'm really happy with them. They have really good customer service. So again, if that's something you're interested in, looking at more of those, they're a great resource for that. Okay, so again, exploring engineering, we're looking at those ideas of investigating. In fact, let me go back really quick to this, right? of how do engineers use tools to solve problems, how the shape of an object is related to its function, right? So the sail, for example, how is the shape of the sail related to its ability to hold the air? That failure is a way to assess success. So when it doesn't work, we learn more about it and we investigate it more and we come up with a better solution. And that engineers use a process known as the design cycle. So all of those things, that's what we're looking at through this module, is that idea of investigating really that, what is it like to be an engineer? And the books that you received on this really highlight some of those careers in engineering. And I think it's really important for kids to have an understanding that there are so many different types of engineers, lots and lots, but they all kind of adhere to the same concept, right? These same kind of premises of being an engineer. Kat asked, can the cars be taken apart and rebuilt by other students? They can, once you start using the reaming tool. The reaming tool opens up that hole to make it easier to put things in. So they still should be able to put the dowel rods in there. It'll kind of already loosen it up, if that makes sense. So they could definitely be taken apart and reused, but you may not need all of the same steps if you put it together a second time. Okay, and our final module that we're going to talk about tonight is fascinating farmers. And recently I sent out the coupon codes for you to receive your worm farm. And there was a little bit of a mix up with their website, but I believe that's all been fixed. And the code that I sent you is your code. It's assigned to your name, and it is for you to order the worm farm whenever you are ready to do so. Okay, so whenever, if you want to order it now, you can. If you want to wait till spring, you can do that. If you want to wait till the beginning of summer, you know, you're going to do it with a summer camp, you can wait till then. It's up to you whenever you would like to use it, but you're going to get worms, you're going to get a worm farm and some tools to help to maintain it. So I just wanted that code is specifically for you, and you can use it whenever you want. But when we're looking at fascinating farmers here, we are investigating some of these ideas that are tied to farming. So these are the kind of those four main things that we're looking at. So the idea that plants have needs in order to grow, which really aligns with a lot of our life science standards, right? And so this is where you might use your root view farm, right? So that the root view farm came with a variety of seeds. It also came with some growing material pucks, and you add water to those pucks so that it expands, and then you can plant the seeds in it. But what's really great too is that you can watch as those plants grow. You can look at the root structure, hence the name, the Root View Farm Kit, and you can talk about what do plants need in order to grow. You also received a grow light, right, with this kit. So you have a grow light, so you have like a lamp holder and a special light bulb that you could use, and that will provide the wavelengths of light that will help those seeds and those plants to grow even better. So you can talk about what are those things that we need to give a plant in order to help it to grow. Also looking at the idea that nutrients are cycled in order to sustain life, that they go through our system, right? These nutrients that are helpful. And this is where we can look at our worm farm and the idea of recycling these nutrients through the worms. So we'll talk about that a little bit more in a little bit. Environmental health affects human health. This is such an important concept that we need to teach everyone, not just our young learners, but how the health of the environment has a direct connection to us. So how do we protect our environment in order to sustain and to protect us as humans? What is the relationship between our actions and the health of the environment in which we live? And then our fourth concept here is that farmers use tools to plant, to maintain, and to harvest crops. So we can look at what are those tools, what do those tools look like, and you can even investigate using tools with your root view farm and even your worm farm. What are those tools and how do we use those tools to sustain? Okay, so I want you to think about this one, since it's focused on farming and we happen to be a state that has a lot of farming. What are some phenomena or provocations that we can use for this? Okay, thinking that some of you live in very rural communities and your students might be quite familiar with farms. They may have grown up on farms or work on their farms and their family members work on that farm. Some of you may be in very urban areas and your students may not have a relationship with farming or understand how it's related to our state and to our economy and where we get food from. So just think, and if you have some ideas, you can put those in the chat room, but what are some phenomena or provocations, right? Remember we said those are the seeds, literally the seeds that we talked about in learning for our students to begin to grow them as a scientist. So I want you to think about that. And if you come up with some ideas, you can put those into the chat room. In the previous page, there were some examples here of some provocations or some phenomena that you might use. But it's so important when we think about that flower graphic that we always begin with something that begins our students to question and to think and to be curious and to wonder. So how do we begin that process around the theme of farming and agriculture? How do we get them to be curious and to wonder and ask those kind of questions and generate those questions? What are those scenarios that we can set up that will allow them to do that? Okay, so I want us to keep thinking about that. If you have some thoughts and ideas, you can put those into the chat room. But I want to show you some ideas that I have here. And agriculture is not necessarily directly listed in any of our standards, whether you're talking about GOLD, Iowa Early Learning Standards, or even the Next Generation Science Standards or core standards that we have. You won't see direct ties to farming or agriculture. But that doesn't mean it's not related to those standards. So I wanted to show you an example here. So this is a kindergarten standard for life sciences, and it says use observations to describe patterns of what plants and animals, including humans, need to survive. So imagine with your kindergarten students, if you're investigating this idea, right? Observations to describe patterns of what plants and animals need to survive. And we can investigate that through the balance between your worm farm and your root view farm, or any other kind of way that you might be growing plants. Because the intention of the worm farm is that we're going to take materials that are otherwise might consider them waste, right? So they might be food scraps. I'm going to show you a chart here in a little bit of what can go into your worm bin, but things that we might consider waste. And worms are then able to take that waste material and break it down into the organic components, the molecular components that they are made of, and return that to the soil. Then plants draw those nutrients up through their root structure, right? Through our root view farm, for example, they draw those nutrients up and use that to grow their roots, their stems, their leaves, and their fruits, all of which are edible in some capacity, right? So different plants have different parts of them that are edible, but the potential is there that some plants, when we eat them, we're eating the root. Okay, so a root structure, perfect example is a carrot, right? So you're eating a root structure, or a sweet potato is a root structure. We might eat the stem. Celery and rhubarb are great examples of stems. We might eat the leaves. So lettuce, for example, would be an example of eating leaves. Spinach would be another example of that. Kale is us eating leaves. And we might eat flowers, right? We might eat blossoms. So broccoli is an example of eating flowers that just haven't quite bloomed yet. That's an example, and you can certainly eat other types of flowers, edible flowers. And then we can eat the fruits or even the seeds that come out of there. So we then take those nutrients as animals, we eat those, and then we discard different pieces or remnants of that, and we begin the cycle all over again. This is such a powerful message. And students, even our young students, can understand this concept of recycling. And this module, Fascinating Farmers, really truly lends itself to understanding that idea of nutrient recycling and how important really that is to our state. So I want to talk a little bit about the worms, because those tend to be something that creates some anxiety for some educators and for some students. So I want to show you just a little video. This is a little young friend who is investigating worms coming out of the bag, similar to the bag that you will receive. And this actually, this supplier, it's called Uncle Jim's Worm Farm. We used them last year, but this year we're using Squirm Farm. But I just want you to notice how this young friend is interacting with the worms and how his mom is encouraging him to do that. And that even though for you personally, the worms may be gross or disgusting, we need to not convey that to the students. They need to see these worms as something they're going to investigate, learn about, and care about, and take care of, right? We don't want them to think that they're gross and we shouldn't touch them and they're scary. So if you yourself have some anxiety around the worms, it's really important that we not convey that to the students. So let's just watch this little friend as he's investigating some of these worms.
What's in there?
Worms.
Worms? Can you reach in? Let's see. You can pull them out. We're going to put them in the worm farm.
Gee.
Uh-huh.
Yeah, just like when Grandpa and you and I were out there.
What do you think?
A worm.
Worm, what does he feel like?
He feels like touch.
Oh, you're gonna weigh him?
Look what he got.
He doesn't weigh much. You look for some more? Lucia, do you wanna get the worms out too? I like how you're holding them very gently. How many do you have there?
3.
Oh, boy, I think we have a lot more. I think we have a couple thousand in there.
Zebra.
Yeah, those are worms, Lucia. You can put your hands in there too? Okay, let's let Lucia touch some. Here, Lucia, you want to touch those? Or you want to reach in the... Sure, you can reach in. We have to be gentle. We can put them right here, and then we'll move them to our worm farm. Whoa, what do you think? Worms, Lucia. Uh-oh. All right, guys, let's put them in our worm farm.
Okay, so I love the natural investigation by this young friend and how he's curious about the worms. And then I love how they put them on the scale and noticing that one worm doesn't weigh enough to be registered on the scale. So we might investigate, how can we figure out the weight of a worm? So I'm just going to leave that thought with you. I want you to think about that. If one worm can't register on the scale, right? So you have a scale, you have a food scale that came in your Science Sprouts kit. So if one worm isn't registering, how can our students have an opportunity to weigh the worms? I want you to think about it, and if you have any ideas, you can put those into the chat room of how we could use that tool. Also, I think you could use your digital microscope, right, to look at these worms up close and investigate them. We're going to look at this book here in just a moment that will tell us more about the anatomy of a worm and they are fascinating to learn about. And these students can definitely engage with and help to take care of and maintain. You know, they can become basically like a classroom pet. And also a chance for us to learn more about recycling. So I put up here, this is a PDF file that is from the Squirm Firm website that you can go to. This is the same website that you would go to order your worms. And you can get this PDF, and I think this is super helpful to understand the kind of things that you can put into your worm bin and your worm farm, and the kind of things you really shouldn't. And I think when we had a worm farm we prototyped this in our 3-year-old classroom at the preschool at the Science Center, and they did a lot of investigation of what they put into the worm farm and how they watched it every day to see how that material got broken down and turned into something else. And then the students could kind of keep track of what they put in there. So you can see here on this list, what would be considered perfect worm food, right? So these kind of fruits and vegetables right here are great to put into your worm bin. So they could be scraps, leftovers, pieces, you know, things that, you know, if they want to bring them to recycle from home, they can. But there's also some interesting things down here that we see that are not food. So we see cardboard, shredded paper, and egg cartons. And these would need to be the paper egg cartons, not the styrofoam egg cartons. Now, if you're working with some older students, and maybe your younger students might ask this question, how is it that we can put all of these plant-based items in our worm bin, and then we can put cardboard and paper? This might be an excellent opportunity for students to experiment and investigate, maybe even have a project based on what cardboard, shredded paper, and egg cartons are made out of. And they may come to the understanding that they are made from fibers that originate from wood, which is basically a plant. So cardboard, shredded paper, and egg cartons are also plant materials, just like the other things on the list. Down here, you see also a list of things to feed them in moderation. So don't give them too much of potatoes, bread, rice, pasta, pancakes, and pizza crust, right? So these are a little bit more complex carbs, and they can be broken down by the worms, but it takes them a little bit more. And if you're putting a lot of bread in there, it can overwhelm them and they won't get to breaking it down in time, and then it will start to mold. It can actually make the worms sick. So you don't want to put too much of those in there. And then there's a list here of the definite things you don't put in there. And I really appreciate that they put number 1, citrus fruits. So we do not want to put orange peels or lemon rinds or things like that, limes, in there because they have a really high acid content to them. And that can be very harmful to the worm bin and throw off the pH of the worms, or the material that the worms are living in. So we want to stay away from putting those things in the bin. Then you see other non-biodegradable materials, no meats, bones, eggs, eggshells, dairy products, pre-packaged food. So maybe some of their snacks and things we don't want to put in there. Definitely no gummy worms in our worm bin. And things that are very spicy, salty, greasy, or fatty. So things that have a lot of seasoning. If it's got a bunch of ketchup on it, don't put it into the worm bin, okay? Because that can be harmful to them. And also things like pet waste. We don't want to be putting any manure or other fecal matter into the worm bin. Then it talks also a little bit down here of things that you can add. We want to maintain the moisture. That's very important. So I just think this list is really good. Also, what's really good is the books that you received. So you got this book, Worms Eat My Garbage. So how to set up and maintain a worm composting system. I will tell you, if you did not receive Fascinating Farmers, there are lots of directions online for how to make your own worm bin. And you can buy these little red wigglers online. You can also buy them at stores that sell fishing materials. You know, you can, at Casey's a lot of times, you can buy these worms because they're used as bait. but this book is very, 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 very good. And it is helpful, and it gives you lots of directions about how to build it, how to maintain it, what to happen if something goes wrong, if you start to see little mites on here, what to do, like maintaining the temperature. So this book is a really great book to give you directions and kind of that guidance, especially if you've never done a worm bin before. This is a really great resource for that. Okay, worms eat my garbage. And then, yes, I see that somebody was talking about We Dig Worms. I fell in love with this book as soon as I saw it, and love that. I don't know how many of you noticed, but when you open it up in here, he says, the author and illustrator of this book said that this is for my wife, Mama Pat, who asked for a fun worm book to read at the library. And he intentionally did all of his art on paper bags because he was talking about the importance of recycling. So this is a really, really wonderful book that introduces kids to worms and talks about what worms do that are helpful to the environment. But one of my favorite things right here is kind of this anatomy of a worm. And it talks about the outside of the worm, the inside of a worm, and the different parts and pieces. So students could even compare this to themselves. So what does a worm have that they have, right? So they can make a comparison and even contrast. They can understand what happens to the food. So as they move through this composting material, that it comes through here and then it comes out the other end. And that material that comes out the other end, which they might use the word poop, and we can all laugh and giggle about that, but that material is actually very rich in organic nutrients and is really good for plants and other things. They will have new worms that are growing in there, and the worms will regenerate. Some of the worms will die. You most likely are not going to find dead worms because they decompose and the other worms help to break them down. I know that sounds kind of gross, but that's just how the process happens. But I just think this is a really good book that does a good job of talking about kind of a story of a worm, but also helps us to understand the importance of worms and what they do for our environment. So this was in the book too, but I want to show it to you. Here we go. I love this little picture right here about the worms talk about how my poop is good for the soil, and it's known as castings. And I'm telling you that because you will see in some of these other reference books like this and online, they'll talk about worm castings. That's what they're referring to, is that waste product as the worms eat the material. The castings right here, that's that organic rich nutrient material that you could then transfer to a planting device like your review farm, or if you have other pots or plants. So your worms could be generating all this material now over the winter, and then in the spring you could do some kind of planting project and use the material from your worm bin as the basis for planting those seeds. Wouldn't that be amazing for your students to see how the food scraps and the cardboard and all these things that these worms have been breaking down over the winter can now be translated into new plant material in the spring? Okay, and it's that idea of cycling of nutrients that we're really trying to get them to understand. Okay, and as I was showing you earlier, that is definitely, let's see if I can go back, that is definitely aligning with our standards. This is just one standard that I pulled, it's the kindergarten standard, but it definitely reaches for sure into the upper grades, but the idea of cycling, of recycling and patterning will definitely support the standards for your students. Okay, so that brings us to the end. And what I want to do, we just have a few minutes. So if you have, first of all, I wanted to see if anybody had any ideas of how you might measure worms. So I want to see if you have any ideas of how you might measure worms, the weight of a worm, even though one worm doesn't register on the weight on the scale. So I didn't see any ideas in the chat room, but I hope you were at least thinking about it. So did you notice how our little friend was adding multiple worms to the scale? So what you could do is put a number of worms on there to the point where the scale can register the weight of it, and you can have them counted out. So it might be 10, depends on your worms. You know, it could be more than that. And then what we could do is we could use that as a volume of measurement. So you could even call that one worm weight, okay? So 10 worms, it takes 10 worms to come up with one, right? And we could, if we wanted to, and so if you have 20 worms, then that would be two, whatever you want to call it, whatever term you want to give to that measurement of weight. Or we could do some math, and let's say that 10 worms weighs 1 gram. So then we could divide that and say that it's 1/10 of a gram is how much this worm weighs. And you could measure various worms of different sizes and see what they weigh. Or you're receiving, I believe, a pound of worms. So you can even start with that mass, with that weight if you wanted to, and see how that changes. I love, yeah, you could use the ruler for length. It would be a little challenging to get the height, but you could. You would have to really look at those really small lines of measurement on the rulers that you received, but you could do it. Maybe some of your older friends that maybe come to visit students could help to measure that. Like if you have, you know, 4th grade buddies that come down to your preschool, or if you have adults in the room that can help them to measure that. Or we could just use and focus on length and see how long our worms are. And then maybe we might observe how they move and how they interact with each other. I will tell you that if you choose to take the worms out for a period of time, don't leave them out for too long because their skin needs to be moist. Something you'll learn in the We Dig Worms books is that worms breathe through their skin. So if their skin gets really dried out, they aren't able to breathe. So it would be important, if you're going to have the worms out for a longer period of time, you could put them on a wet or moist paper towel, or you might use like a spray bottle just to keep the area moist so they don't dry out. Otherwise, keep putting them, you know, kind of recycling them and putting them back into the worm bin, and maybe taking some other worms out so that they don't dry out. If you maintain your worm farm for a long period of time, you will have lots of worms, probably more worms than what you started with. So you may want to have a plan of how to share the wealth of worms. And so you may come up with a project where maybe students take some worms home, and they can, as long as they have a place, an outside place where plants are growing, bushes, flowers, trees, they can put those worms into the ground. They're not going to hurt anything. They're not going to contaminate anything by putting those worms in there. Or they could start to maybe begin to generate their own worm bin. So something to think about and keep in mind as you maintain your worms is they will reproduce and they will make more worms, and you will definitely want to monitor that as you move forward. So we have come to the end of our last webinar. I know 2 hours is a really long time to sit and take in a lot of information, but I hope that you found this useful. And what I truly hope is that you think about how are we growing young scientists in the work that we do? How are we providing students an opportunity to explore, to have that curiosity and wonder, ask questions and investigate those questions? I'm going to bring us back to, hopefully, maybe our flower graphic. Maybe not. But I just want to remind you of that idea that we want to provide for our students opportunities to investigate and authentically go through and learn how to be a scientist. This is where I'm trying to get. Here we go. right? So we always want to provide some kind of experience that begins that process, that seed, that gets them excited. And then we want to water that seed by helping them to ask questions and supporting them as they ask questions. And then we're going to help to grow that experience by helping them through an investigation. So providing them tools and materials and support to collect data or to analyze things or find out more information. Then we will see the blossom of that work through their understanding, through their authentic representations, their project work, their general results to what they are investigating. And then to really complete that process, we want to harvest that. So how are we sharing that? How are we reflecting on it? You know, it could be through some type of celebration. It could be through a digital platform. There's lots of different ways that we can harvest that understanding, but it's really important that we provide that opportunity. So, if you have any questions as you progress throughout the year using your pint-sized science materials, please let me know. You're welcome to always send me emails and ask for supports and ideas. I will keep updating things on the website as people ask me more questions. I put more things on there, supports for you. So let me know if you have needs related to that. And I wish you great opportunities to investigate and grow our young learners and through using pint-sized science, right? So thank you. Enjoy the rest of your evening.